electromagnetic field and induction being used for telecommunications. Now we're talking about power distribution. And if we scan down the page, you can tell that we're leading towards power distribution because look, we got some sort of an electrical tower thing going on down here. Okay, so that's what we're working towards, is the theory for that. So the result of coils producing fields and fields inducing current is that current can indirectly be transferred to a secondary electrical coil. Now, previously, with the telecommunications model, we actually talked about current being transferred to a secondary electrical coil directly. It actually was wired to connect. This is indirectly, and we do this through a transformer. And when I say indirectly, I'll show you what I mean in a minute, okay? All right, so this here is a diagrammatic model of a transformer, okay? And we're like 2/3 of a page away from the end of the note. And in a minute, in real life, I'll show you like an actual transformer. But you've seen these things around the neighborhood. You ever see it, the gray boxes that are at the top of the electrical poles, or the green boxes that are in people's front yards sometimes, depending on the age of your neighborhood? Those are the transformers, okay? Now, inside of your homes, there are actually transformers as well. And so in terms of talking about now in our area, there happens to be a regional step-down transformer. And if you don't know where it is, I mean, here we are in Burlington, but here's a Google Maps shot. And if you want to, you can find the latitude and longitude and you can locate it for yourself. But it's tucked in behind IKEA. There's a regional transformer station, okay? And usually if we have a power outage in the summer, those transformers have overheated. There's been some, you remember we said transformers, solenoids vibrate at 60 hertz. That's somehow one of them's broken down. The insulation around the housing has worn out. And if you're going to see anything when the power goes out, you often see like smoke rising from a site just behind IKEA. And this is the reason, okay? It's because that one of those transformers is gone, okay? That means that we end up having disruption to our power distributions. Anyway, what happens around the province is that at the local or at the provincial, one of the stations around the province, is we produce electrical energy using whatever form, whether it's nuclear or Niagara Falls or wind power, whatever it is. And then that electrical energy has a step-up voltage, goes up to something like 240,000 volts. Then you see these electrical towers, the electrical tower conduits that travel through the neighborhood. Underneath of them, often there are like bike paths or something, but there are towers, right? So we try to like recoup the space as natural space by having bike paths or something to, let people walk their dogs or whatever. But if you look up, you'll see these towers. These towers carry electricity at high voltage. Why does it carry at high voltage? We can come back to this later, but it really is because high voltage electricity transports more efficiently. So it's really about cost. Then later on, we get down to the step-down transformer, the regional step-down transformer, like say that place behind IKEA that I was mentioning, and it takes it down to 2,400 volts. Every once in a while, you hear about somebody going into one of those transformer areas. There's one out towards Winona, I think, and there's one near where my aunt lives, out towards the Niagara area. Every once in a while, you hear about somebody dying in one of those step-down transformer areas, and it's because they're trying to get into the transformer area, which, by the way, is really well fenced off with barbed wire and everything, which is just a challenge to some people. And when they say challenge accepted, what they're trying to do is get the copper wire out of the transformers so that they can sell it to the scrapper. They may get a few dollars, but at 2,400 volts, this is why some people die. Don't go into those areas. This is dangerous. Anytime you see high voltage, do not enter. It's not a challenge. It's, survival of the fittest, I guess. Turn back, all right? When it gets to your neighborhood, there's another step-down transformer, which is either at the top of a pole or in a green box in your front yard, and it takes it down to 240 volts. When it comes to your house, at least in this region, 240 volts is the voltage that enters your home. Now, we keep it at 240 volts when it enters your home because that's the voltage that we're going to run our electric dryers off of, our high voltage devices. Like for me, I got a couple of 240 volt heat lamps in my backyard so that I can enjoy the patio well into the fall, And that's lovely. But the rest of my outlets don't run on 240. The rest of my outlets run on 110 to 120. And so that's what all of our plugs in the walls. If you plug something into the holes, typically it's the 120 to 110 volts. Okay, so it runs within that range. People will often say 110. Notice that these guys are all sorry. Let's typically say 110 because that's like the mid range between 100 and 120, which is the acceptable range for voltage. But 120, you'll notice, is half of 240. 240 is one half, one hundredth, sorry, 1/10 rather of 2400. And you notice that there's going to be multiples of that 120 throughout all these numbers, right? Now, the fact that there are multiples of 120 all through these numbers is going to be a consequence of what we're going to talk about in just a second here. The fact that the number of coils on the primary coil and the number of coils in the secondary coil is going to be a ratio. We're going to talk about that as a ratio. And so we use these transformers as step-up transformers and step-down transformers. And the step-up happens to obey a ratio rule that is related to the number of coils on the primary versus the secondary. And the step-down likewise, right? So it's a fraction issue. So that's an issue. So if it steps down from 2400 to 240, there must be a 10 to 1 ratio of the number of coils. Am I selling that idea? And the reason that we would have a ratio of number of coils is because I can transmit energy from this one to this one, and there's going to be a magnetic field induction in the secondary coil. Okay, so let's talk about what's going on. And I think that we need to do this almost as like a step-by-step, but I have one picture, and I want to do it as like a 4-step process, so not as a comic strip, okay? So I'm going to number my steps. So step 1, current turns on. Now, I'm going to say that this power source looks like a DC source, just the way it's been drawn, only just because most of you aren't familiar with the symbol for a DC schematic source. I'm just going to say it out loud. This is an AC source. Okay? Somebody who's really into electricity is going to say, that's not the symbol for an AC source. I know. But at this snapshot in time, this AC source has positive terminal here. I know that a moment later, it'll become a negative terminal, okay? For now, for this snapshot in time, it's positive. And somebody else online will probably say, this can't even work with a DC source. To which I would say that's true. And we'll talk about why shortly. All right? So in the moment where this current is going this direction, it would be coming out, obviously, this direction. But let's talk about what's going on in the coil. In this coil, that means that I'd be having current coming out of the page on this side of the solenoid and going into the page on this side of the solenoid. And that means that this coil, this solenoid, is going to have polarity. Can you guys use your right hand? Which end of the solenoid at this moment in time is north? People are mouthing top, right? Yeah. North, south. That's just the solenoid. Now, this solenoid has an iron ring core going through it. And what that means is, this is step number 2, that the domains inside of that core are getting aligned so that they're aligned with the solenoid. See how the iron itself is going to get polarized? Right? We've talked about polarizing a core before. This is just a weird shaped core. So let's say that this is step 2. I'll put it up here. Step 2, domains within core align. What's that? Well, at this point, I'm not talking about the purpose. At this point, I'm just saying that they do align. And if we can swallow that as an idea, we'll get to that in step 3, okay? Why would we want them to align? If we can accept that they do align, that's step 2, all right? So we're trying to chunk this out in the thought process. Because I find that if I present this as a block paragraph rather than a 1, 2, 3 step process, people get lost in the block paragraph. You might imagine, right? We're just talking about it as a consequence of what happens next. Now, and I'm glad you asked, what's the purpose of them aligning? Let's say, if I get all these domains to align, isn't that like shoving a magnet into the secondary coil? So let's call that step 3 then. Step 3 This is like, I'll underline like, shoving a north into the secondary coil. So in my imagination, this is like an animation, but I've heard people say this is starting to feel more like an infographic. Either way, though, are we okay with it? All right. So the next step, now that we've shoved a north into the secondary coil, what's the secondary coil going to do? It'll resist, right? That's what it does. And so if I try to shove in, effectively, I'm trying to shove in north domains into its mouth, what does it try to do? What does the top of the coil become, north or south? Yeah, it becomes north. It resists the incoming domains. So yeah, look, this secondary coil is going to become north at the top and south at the bottom. Now, if it becomes north at the top and south at the bottom, use your right-hand rule again for solenoids. That means that the current's going to go into the page on the right-hand side of this solenoid, and it's going to go out of the page on the left-hand side of this solenoid. And if I map out what's going on with the current, maybe it's hard for you to see the three-dimensionality, but this wire wraps behind underneath of this transformer core. And so that means that the current's going to go this way through the circuit. There's a galvanometer measuring the current flow. And so just for this moment, when I turn this circuit on and this positive current flows, I'm going to get current flowing in my secondary circuit. What I want to point out, actually, maybe let's put this in writing before I point any more out, okay? So step number 4, the secondary solenoid, secondary. I started with the word solenoid. I got ahead of myself. Secondary solenoid resists the incoming north domains and becomes polarized. That seems like a bite-sized enough idea, right? And then as a result, step 5, which I actually kind of already drew and said out loud, is current is induced in the secondary coil. Now, if you can follow this through in this kind of like slow chunked out method, I bet you if you want to see it faster and more flashy, you can find a nice cartoon that explains the exact same thing in about 30 seconds. But I would challenge you that you probably wouldn't take it in 30 seconds. I think we've taken it in about whatever this is, 10, 15 minutes, right? It just takes time to kind of digest the idea a little bit. And so hopefully this is helpful. But it seems to me that if I have more coils on one side than on the other side, the magnetic field that I produce through that solenoid is going to get picked up on the secondary solenoid differently, right? That sort of makes sense if I have less coils on the right than on the left. And so what people say is that there is like a ratio issue going on here, but there's also a conservation of energy thing going on here. So if P stands for primary and S stands for secondary, let me zoom in on this. That means that the amount of power in the primary coil is going to be equal to the amount of power in the secondary coil if conservation of energy is a thing. And we all believe in conservation of energy, right? Like energy is not being created or destroyed in a transformer. That's ridiculous. But what we also said earlier was that power is equal to voltage times current. So I could expand out the left side and the right side to be V primary times current primary equals V secondary times current in the secondary. And what that means is that if I isolate to get the voltages on the left-hand side, it would be V primary divided by V secondary, and it would be I secondary divided by I primary. Now, the reason I wanted to do sort of like the quick preamble to get up to this and then finally write this in handwriting is there are some people that think, oh, you wrote the equation wrong. On the left-hand side, the P's on the top, and on the right-hand side, the P's on the bottom. No, that's just the way the ratio works out. Okay, and you can see that it's really as a consequence of this conservation of energy thing and isolating for the V's. And people say, well, why would you want to have the V's isolated and the I's isolated? Well, it again seems to me that I could use a voltmeter sometimes and an ammeter sometimes. And, I could solve the left-hand side ratio using my voltmeter and the right-hand side ratio using my ammeter. Now, the other thing is, because this, maybe I'll put this in writing because I didn't really put it in writing, power in equals power out is because of energy conservation. But we also said that somehow the number of coils is related to the voltage and the current in a solenoid for these things. And what we say is, yeah, for sure, Vp over Vs is equal to Is over Ip. But because there's a proportionality with the number of coils to the voltage, we said that earlier with the wiggling hand and the magnet, it means that the number of coils in the primary over the number of coils in the secondary is also equal to this ratio. Number of coils. Oops, sorry, chopped off. Number of coils. And so I said earlier that the step down and step up transformers at these various stages of the electrical grid, the step down and step up happens because of the ratio of number of coils in one versus the other. Look at this. If I say this is kind of a triple equation, can you see that Vp over Vs is equal to Np over Ns? That ratio of coil numbers actually steps down the voltage fraction-wise, okay? And so if I want to step something up, I would want to have the number of coils make it so that there's more voltage in the secondary. If I want to step the voltage down, I'd want to make sure that I have more in the primary. Cool? All right. That's just like a quick little talk about that. And maybe I'll zoom back out again for people that missed something so you can kind of have it all on one page. But I also want to pause to see if there's any questions. Anybody got any questions about like the conversation here? Yeah.
So on the secondary coil,
yeah.
Which way is the coil going in the foreground?
Oh, so in the foreground, maybe I'll apply a little bit of white out here just so we can see it, just in case you can't see what's happening with this coil. Put a little white out on there so you can see that it's wrapping in the foreground in front of the coil. And maybe my contrast isn't very good on. Let's see. Grab your right hand. Did I make those guys go the wrong way? Oh, shucks. You guys are so polite. Good catch. Did you fix it on me? No, you're right. I was seeing it wrong when I was talking. You're absolutely right. I see it now that you forced me to see it. All right, so you're right. The current will be going into the page on that side. I mean, it doesn't change the conversation we're having, really, right? It'll be coming out of the page on this side, but it does highlight how careful you have to be when you're looking at these things. And so that's going to be, as a consequence, it's going to mean that at this snapshot in time, all that current is going the other direction, isn't it? It doesn't change any of our descriptions, though, okay? Right. Wait a minute. Did I have the current going the right way? Oh, I guess it does still go that direction, doesn't it? Is that right? Yeah. Yeah, this X means it's going into the page on the bottom, right? Yeah, the X's and the dots were wrong. The arrows. Wait a minute.
The X's and the dots were right, the current was wrong.
Oh, you're right. Oh, the X is, it was. Oh my. Well, you know what? I'm not even gonna cut this out of the video. I'm gonna leave it in there for other people to enjoy. All right. So yeah, you're right. It's the, now I got it. The dots. The knots were correct. Oh man, my pen's even getting clogged up on whiteout now. No, we had it. All right. People watching the YouTube video are like rage quitting right now. All right. All right. See, this is why we do things live. Going up through the galvanometer.
Can you show the right hand for this?
Like actually get my right hand out?
Yes.
Yeah, I got a right hand handy. So for the secondary coil, we'd be talking about our hand grabbing that secondary coil like this, going into the page on the right hand side, out of the page on the left hand side, which means that the current's going to be going to the right in the foreground at the bottom there. Yeah. All right. Thank you for asking.